Hey everyone, today we're going to look at reciprocal functions. I've gone ahead and chosen our f of x to be 1 over x minus 2. I have a table of values and also a place where we will roughly sketch the graph. In order to understand reciprocal functions and why the graph looks the way that it does, I think we have to first begin by looking at our function 1 over x minus 2 and find our non-permissible value. So if we look at 1 over x minus 2, x cannot equal positive 2, and we want to know how that will display on our graph, or maybe even algebraically in our table of values. So let's go ahead and actually see how f of x looks when we kind of get close to positive 2. So I'm going to start with 0, 1, 1.5, 1.9, 1.99, 2, 2.01, 2.1, 2.5, and 3. And so there's a little bit of symmetry behind this. It's really important to note that right here we're actually going to get an error. We can't actually do f of x when x is equal to 2. That's why it's a non-permissible value. But I really am interested in what happens before we get to 2 and then what happens immediately afterwards. And so in order to do that, I think the best way to go about it is to just get out our calculator and start actually calculating what those f of x values are going to be for x. So let's start with x is equal to 0, so we're going to have 1 divided by negative 2. 0 subtract 2 is negative 2. So that's negative 1/2. Okay, and so then 1 subtract 2, that's negative 1, and 1 divided by that is going to also be negative 1. Okay, so what about 1.5 subtract 2? And then 1 over that answer. So negative 2 here. Okay, what about 1.9? Well, 1.9 subtract 2, and then 1 over that is negative 10. Okay, 1.99. Negative 100. Okay, so it seems that before we actually hit 2, the f of x values are increasing in a negative sense as x gets closer and closer to 2. What about right after 2? Okay, so 2.01 will get positive 100. I wonder what we'll get for 2.1. Maybe you already guessed that you're going to get positive 10. And so therefore we can see a lot of symmetry here. The next I should get is positive 2 and then positive 1. So this tells me a lot of these f of x values, I really want to look at what happens before and after. And maybe we can even go one step further here. I can do 1.999, let's do 4 nines actually, subtract 2, and then 1 over that number. It gives me negative 10,000. So this is getting very, very, very big the closer I get to 2. The same can be said regardless of which way you approach 2. So this would be approaching it from the left, is what we say, and this is approaching it from the right, as these values are to the right of 2 on our graph. So here's 2. And we have a few other points. We can say, okay, 0 is negative 1/2, so maybe we'll plot that right here. 0 is negative a half, and positive 1 is negative 1. And then the closer I get to 2, the bigger the f of x values get. So what's happening is I'm getting a graph that looks like this. And it will keep going down and getting bigger and bigger negatively. However, it will never actually have a value at x is equal to positive 2. So conversely, as we move away from positive 2, this gets very, very small, but still a negative number. As we approach positive 2 from the right, we know that when x is 3, f of x is 1. So we can say that this is the way the graph looks. It gets bigger and bigger positively, but it never actually has a value when x is equal to 2. So the way we represent that is often you'll see me draw a dotted line. This represents that we are approaching that line, but we're never actually going to occupy it, if that makes sense. This whole idea has a fancy name, this algebraic behavior, and then this graphical behavior here. This is called a vertical because it's up and down, and the fancy name is asymptote. Sometimes I'll refer to it as asymptotic behavior. So a vertical asymptote is a vertical line which your graph approaches but never actually touches, if that makes sense. You may also be wondering, well, does this graph ever touch the x-axis here? And there's a couple ways to figure that out. However, we can kind of look at this the same way we looked at what happens around 2. And so I often would say this is kind of like a critical point to look at, is what happens as x gets very big positively, let's say. So what's a very big positive number? Well, we can say 15,000. That's a very big positive x value. If I take away 2 from it, it's still pretty big, and I do 1 over that number. 6.667-ish times 10 to the negative 5 is a very, very small number. You'll also note that it's a very small positive number. So let's try one more. Also a very small positive number. So this is approaching 0, but it's never actually going to be 0. And we can kind of look at that in an algebraic sense as well. Imagine that I asked you to solve this, because that's what we're looking for. When is the y value, or when is f of x 0? To solve this, you might say, okay, let's multiply both sides by x minus 2, but 0 multiplied by anything is still 0, and we maybe end up with this. This is kind of telling you that f of x isn't going to be 0. It's not liking this. And so we have another name for that. It looks like it's approaching 0, but it never actually touches it. This would be called a horizontal asymptote. We would say horizontal asymptote at y is equal to 0. Okay, so that's kind of a rough sketch of what our graph looks like. We have this new idea of asymptotic behavior. Let's try another example. Let's try f of x is equal to 1 over x squared subtract 9. Okay, well, as soon as I write that, I realize it's a difference of squares, so let's just very simply factor it. Gives me a better picture that x cannot equal positive 3 or negative 3. Now, before, it happened to be the things on the bottom of the fraction here that translated to non-permissible values, which also translated to our vertical asymptote at x is equal to positive 2. So these non-permissible values of our new function are also our vertical asymptotes. So we have a vertical asymptote at x is equal to positive 3 and x is equal to negative 3. We're going to have two vertical asymptotes. Okay, so I'd like to take a look at some critical points here. I want to look at, well, I want to look at negative 3. I want to look at 0. I want to look at positive 3. And the reason I want to look at 0 is because that's what's in between negative and positive 3. So I'm going to look at those points. As I kind of think about them, I'll draw myself a very rough sketch of a graph here. I'll say, okay, here's positive 3. Here is negative 3. We have our asymptotes. And let's start by calculating x is equal to 0. So that's going to be 0 plus 3 multiplied by 0 minus 3, and then 1 over that number. So that's negative 0.111 repeated. I recognize that as negative 1 over 9. And the key point here is that it's negative. So at x is equal to 0, it's roughly around here. There's no scale, so long as it's below 0, that's fine. That's what we're looking to try and figure out. The other aspect is that this is going to have a horizontal asymptote at y is equal to 0. I can tell that because imagine like if I tried to set that equal to 0 and solve. It's the same problem we ran into last time. So this point here is going to approach positive 3, but it's not going to cross this and go up like that because it can't actually touch the horizontal asymptote. So the only other option here is for this to go down like so. And it's going to do that on both sides. Again, very rough sketch. And that's kind of like a logic piece behind why the shape of the curve has to be this. I can also double check by inputting a value of maybe 2.5, let's say. So we have 2.5 plus 3 multiplied by 2.5 minus 3, and then 1 over that number. So what I find here is that it's still negative. Maybe we try 2.9 plus 3 and we get still negative just below 2 here. So I think what's important to note is that it's still negative, and it's getting bigger. So it's approaching negative infinity, we might say. Then maybe we try 4. 4 plus 3. So I want to know actually what happens over here. 4 plus 3 multiplied by 4 minus 3, positive number, and then 1 over that. Still positive. So over here, it looks to be doing this. So the whole curve has a sketch, looks like so. If I did the same thing around negative 3 to the left of it, I would find the same thing, as it would be symmetrical to over here. So this is what our sketch looks like based on our function. And so really, when I look at this, I examine what happens around those points that I can't have. I examine a little bit above them, a little bit below them, and if there's 2, most certainly in between them. Let's take a look at this for on Desmos, just to kind of reiterate a few things. So we'll start with the 1 over x minus 2. So that we have there, and we have a vertical asymptote at x is equal to positive 2. So that's a little bit about what that looks like. So that's exactly what we graphed in that first example. I guess the reason I want to kind of do this is to check that we're right. That's what graphing technology is for. But I also want to look at that horizontal asymptote. What could possibly change that? And it turns out that if your function looks like this, and then kind of tagged on at the end is like a +2 or a -1 or something, a constant like that, then the graph shifts upward too. And so now the horizontal asymptote would be y is equal to +2. And I want to reiterate that our graph approaches this line, but as we move further and further into positive x values, at this point we're at 11, it approaches but never quite touches that line y is equal to +2. That's a kind of definition of an asymptote. Let's look at a few others. We'll check that our function there was correct. So, I mean, ours was a bit of a rough sketch. It doesn't seem to drop so steeply here like we drew, but for the most part we got the characteristics of the curve right. So that's kind of what our function looks like. And we can kind of keep doing that. There's no reason why we can't have a cubic on the bottom. And we just have more asymptotes and more points to examine. The kind of nice thing is I often think of this as kind of a mashup of different reciprocal functions. One where the asymptote is around +3 caused by this. Another reciprocal function where it's around x caused by, where the asymptote's around x is equal to 0 caused by this one. And then all the way over, it's almost like you have 3 individualized reciprocal functions all meshed together into one. And every time you go from one side of an asymptote to another, it flips positive to negative or negative to positive. Again, hope that kind of makes sense. That should be everything you need to know about reciprocal functions.